Welcome to our deep dive into alternating current, or AC. In this chapter, we'll explore the essential concepts, formulas, and applications of AC, which is the backbone of modern electrical systems. From understanding what AC is, to learning about RMS and average values, phase differences, and the behavior of AC in different circuit elements, we'll break down each topic step by step. Whether you're a student preparing for exams or just curious about how electricity works in your home, this video will help you grasp the fundamentals of AC with clarity and confidence. Let's get started by defining what alternating current really means. Alternating current, commonly known as AC, is an electric current that periodically reverses direction. Unlike direct current, which flows in one direction, AC changes its direction and magnitude with time, typically in a sinusoidal pattern. This property makes AC ideal for transmitting electricity over long distances, as it can be easily transformed to different voltages. The most common example of AC is the electricity supplied to homes and industries. Understanding the nature of AC is crucial for analyzing how it interacts with various electrical components and for appreciating its advantages over direct current. RMS, or root mean square value, is a key concept in AC circuits. It represents the effective value of an alternating current or voltage, which produces the same heating effect as an equivalent direct current. The RMS value is particularly useful because it allows us to compare AC and DC circuits on the same basis. For a sinusoidal AC, the RMS value is equal to the peak value divided by the square root of 2. This value is what most voltmeters display when measuring household electricity, making it a practical and widely used measurement in electrical engineering. To derive the RMS value of an alternating current, we start by considering a sinusoidal current, I equals I0 sin, megit, where I0 is the peak current. The RMS value is defined as the square root of the mean of the squares of instantaneous values over one complete cycle. Mathematically, it's written as IRMS equals SQRT 1/t integral letter 1d40, I0 sin, megit, 2 dt. Solving this integral, we find that IRMS equals I/square 2. This derivation not only provides the formula, but also helps us understand why the RMS value is always less than the peak value for a sinusoidal AC. Average value of an alternating current is another important parameter. For a complete cycle of a pure sinusoidal AC, the average value is 0 because the positive and negative halves cancel each other out. However, when we talk about the average value, we usually refer to the average over a half cycle. This value is useful in certain applications, such as rectification, where only one half of the waveform is used. Understanding the average value helps in analyzing circuits that convert AC to DC and in calculating the net effect of AC over time. Derive the average value of a sinusoidal AC over a half cycle, we start with the equation I equals I0 sin, megit. The average value, AVG, is calculated as 1/pi I0 sin theta d theta, where theta equals omegit. Solving this integral, we get AVG 2/0/pi. This result shows that the average value is less than the RMS value and much less than the peak value. Knowing how to derive and use the average value is essential for understanding rectifiers and other AC to DC conversion devices. Phase difference is a fundamental concept when dealing with alternating currents and voltages. It refers to the difference in phase angle between two waveforms, such as voltage and current. In AC circuits, especially those containing inductors and capacitors, the current and voltage may not reach their maximum and minimum values at the same time. This phase difference is measured in degrees or radians and plays a crucial role in power calculations and circuit analysis. Recognizing phase differences helps in understanding the behavior of complex AC circuits. When an alternating voltage is applied across a pure resistor, the current through the resistor is always in phase with the voltage. This means that both reach their maximum and minimum values at the same time. The relationship can be expressed as I equals VR, where V is the instantaneous voltage and R is the resistance. This simple relationship makes resistors easy to analyze in AC circuits, as there is no phase difference between current and voltage. Understanding this behavior is the foundation for analyzing more complex circuits. In a circuit with a pure inductor, the behavior changes significantly. When an AC voltage is applied, the current lags the voltage by 90 degrees, or pi/2 radians. The relationship is given by I equals V/omega L, sin, omegit pi/2, where L is the inductance. This phase lag is a direct result of the inductor's property to oppose changes in current. Understanding how inductors affect current and voltage in AC circuits is crucial for analyzing transformers, motors, and many other electrical devices. For a pure capacitor in an AC circuit, the current leads the voltage by 90 degrees. The mathematical expression is I equals V0 omega C, sin, megit plus pi/2, where C is the capacitance. This leading phase is due to the capacitor's ability to store and release energy in the electric field. The unique behavior of capacitors in AC circuits is essential for applications like filtering, tuning, and signal processing. Recognizing how capacitors affect phase relationships helps in designing and troubleshooting electronic circuits. Reactance is the opposition offered by inductors and capacitors to the flow of alternating current. Unlike resistance, which dissipates energy, reactance stores and releases energy in magnetic or electric fields. Inductive reactance increases with frequency, while capacitive reactance decreases. The total reactance in a circuit determines how much the current is reduced and how much the phase is shifted. Reactance is measured in ohms, just like resistance, and is a key factor in designing AC circuits. Impedance is a broader concept that combines both resistance and reactance. It represents the total opposition to the flow of alternating current in a circuit and is denoted by Z. Impedance takes into account the effects of resistors, inductors, and capacitors, and is generally expressed as a complex number. The magnitude of impedance determines the amplitude of the current, while its phase angle affects the phase relationship between voltage and current. Understanding impedance is essential for analyzing and designing all types of AC circuits. An LCR circuit, which contains a resistor, inductor L, and capacitor C in series, the current is determined by the combined effects of resistance, inductive reactance, and capacitive reactance. The expression for current is I equals VZ, where Z is the impedance given by Z equals SQRTR2 plus XL XC2. Here, XL is the inductive reactance and XC is the capacitive reactance. This formula helps us analyze how the circuit responds to different frequencies and how the current varies with changes in the circuit elements. Resonance is a special condition in an AC circuit where the inductive reactance equals the capacitive reactance, causing the impedance to be at its minimum and the current to be at its maximum. This occurs at a specific frequency called the resonant frequency. Resonance is widely used in radio, television, and communication systems to select desired frequencies and filter out unwanted ones. Understanding resonance helps in designing circuits that can efficiently transfer energy at specific frequencies. Condition for resonance in a series LCR circuit is when the inductive reactance equals the capacitive reactance, or XL equals XC mathematically. This is expressed as omega L equals 1/omega C, where omega is the angular frequency. Solving for omega, we get the resonant frequency, F0 equals 1/2 pi square root, LC. At this frequency, the impedance is purely resistive, and the current reaches its maximum value. Knowing how to derive and apply the resonance condition is vital for tuning circuits and maximizing energy transfer. Power factor is a measure of how effectively electrical power is being converted into useful work in an AC circuit. It is defined as the cosine of the phase angle between the voltage and current. A power factor of 1 means all the power is being used effectively, while a lower power factor indicates energy is being wasted, often in the form of heat. Improving power factor is important in industrial and commercial settings to reduce energy losses and improve efficiency. The power consumed in an AC circuit is given by the product of the RMS values of voltage and current, multiplied by the power factor. The expression is P equals VRMS times IRMS times cos phi, where phi is the phase angle. This formula accounts for the fact that not all the supplied power is converted into useful work due to phase differences. Understanding how to calculate power in AC circuits is essential for designing efficient electrical systems and for energy management. Transformers are devices that transfer electrical energy between two or more circuits through electromagnetic induction. The principle behind transformers is that a changing current in the primary coil creates a changing magnetic field, which induces a voltage in the secondary coil. This allows transformers to step up or step down AC voltages efficiently. Transformers are essential for the transmission and distribution of electrical power, making long-distance electricity supply possible. LC oscillation refers to the oscillatory exchange of energy between an inductor and a capacitor in a circuit. When a charged capacitor is connected to an inductor, the energy stored in the capacitor's electric field is transferred to the inductor's magnetic field and back again, creating oscillations. The frequency of these oscillations depends on the values of L and C. LC oscillations are fundamental to radio transmitters, receivers, and many electronic devices that require stable frequency generation. Choke coil is an inductor used in AC circuits to block or limit the passage of high-frequency alternating currents while allowing lower-frequency or direct currents to pass. It works by presenting a high reactance to AC, thus reducing the current without significant energy loss. Choke coils are commonly used in power supplies, radio circuits, and fluorescent lighting to filter signals and smooth out current fluctuations. Understanding choke coils helps in designing circuits that require selective current control. Alternating current is preferred over direct current for transmitting electricity over long distances. The main reason is that AC can be easily transformed to higher or lower voltages using transformers, minimizing energy loss during transmission. High-voltage transmission reduces current, which in turn reduces resistive losses in the wires. This efficiency makes AC the standard for power distribution worldwide. Understanding why AC is favored helps in appreciating the design of modern power grids. Most common AC waveform is the sine wave, which smoothly oscillates above and below zero. This shape is not only mathematically convenient, but also results naturally from rotating generators. The sine wave's properties, such as amplitude, frequency, and phase, are fundamental to understanding how AC behaves in circuits. Recognizing the characteristics of AC waveforms is the first step in analyzing and designing electrical systems. Frequency is the number of cycles an AC waveform completes per second, measured in Hertz, Hc. The period is the time taken for one complete cycle. These two quantities are inversely related. Frequency equals 1 divided by the period. In most countries, the standard frequency for household electricity is either 50 Hz or 60 Hz. Understanding frequency and period is crucial for synchronizing electrical devices and ensuring compatibility with power supplies. Peak value of an AC waveform is its maximum instantaneous value, either positive or negative. The peak-to-peak value is the total distance from the maximum positive to the maximum negative value. These values are important for understanding the voltage or current extremes that a circuit must handle. While RMS and average values are more commonly used in calculations, peak values are crucial for designing safe and reliable electrical equipment. The instantaneous value of an AC signal is its value at any specific moment in time. This value changes continuously as the waveform oscillates. Instantaneous values are important for analyzing how current and voltage vary throughout a cycle, especially in complex circuits. By understanding instantaneous values, engineers can predict circuit behavior at any point and design systems that respond accurately to changing electrical conditions. Phasors are a graphical way to represent AC quantities, like voltage and current. A phasor is a rotating vector that shows both the magnitude and phase of a sinusoidal function. Using phasors simplifies the analysis of AC circuits, especially when dealing with multiple waveforms and phase differences. Phasor diagrams help visualize how voltages and currents add or subtract in complex circuits, making them an essential tool for electrical engineers. Impedance triangle is a graphical representation that shows the relationship between resistance, reactance, and impedance in an AC circuit. The horizontal side represents resistance, the vertical side represents reactance, and the hypotenuse represents impedance. This triangle helps visualize how these quantities combine and how the phase angle is determined. Understanding the impedance triangle is useful for solving AC circuit problems and for designing balanced systems. Power triangle illustrates the relationship between real power, reactive power, and apparent power in an AC circuit. Real power does useful work, reactive power oscillates between source and load, and apparent power is the combination of both. The power factor is the cosine of the angle between real and apparent power. This triangle helps in understanding how efficiently a circuit uses electrical energy and in identifying ways to improve power factor. AC circuits can have different types of loads: resistive, inductive, capacitive, or a combination. Each type affects the phase relationship between voltage and current differently. Resistive loads keep current and voltage in phase, inductive loads cause current to lag, and capacitive loads cause current to lead. Understanding the nature of the load is essential for predicting circuit behavior and for designing systems that operate efficiently and safely. AC circuits can be connected in series or parallel, just like DC circuits. In series circuits, the same current flows through all components, while in parallel circuits, the voltage across each branch is the same. The analysis of series and parallel AC circuits involves calculating total impedance and understanding how voltage and current are distributed. Mastering these concepts is crucial for building and troubleshooting complex electrical systems. Resonant frequency is not just a theoretical concept, it has many practical applications. In radio and television receivers, resonance is used to select specific frequencies. In power systems, resonance can cause unwanted voltage spikes, so it must be carefully managed. Engineers use resonance to design filters, oscillators, and frequency-selective networks. Understanding how to apply resonant frequency is key to many areas of electronics and communications. When electricity is transmitted over long distances, some power is lost as heat due to the resistance of the wires. These losses are proportional to the square of the current. By transmitting electricity at high voltages and low currents, AC systems minimize these losses, making power transmission more efficient. Understanding power losses helps engineers design transmission lines that deliver electricity reliably and economically. Three-phase AC systems are widely used in power generation and distribution because they provide a constant flow of energy and are more efficient than single-phase systems. In a three-phase system, three alternating currents are offset by 120 degrees, ensuring that power delivery is smooth and balanced. These systems are essential for running large motors and industrial equipment. Understanding three-phase AC is fundamental for anyone working in electrical engineering. AC generators, also known as alternators, are devices that convert mechanical energy into electrical energy using electromagnetic induction. As the generator's coil rotates in a magnetic field, it produces an alternating voltage. The frequency and amplitude of the generated AC depend on the speed of rotation and the strength of the magnetic field. AC generators are the primary source of electricity for homes, industries, and power grids worldwide. AC motors are machines that convert electrical energy into mechanical energy using alternating current. They are widely used in household appliances, industrial machinery, and transportation. The operation of AC motors depends on the interaction between the magnetic field produced by the stator and the current in the rotor. Understanding how AC motors work is essential for designing and maintaining a wide range of electrical devices. Capacitive and inductive circuits behave differently under AC. In capacitive circuits, current leads voltage, while in inductive circuits, current lags voltage. These phase relationships affect how energy is stored and transferred in the circuit. Understanding the differences between capacitive and inductive circuits is crucial for designing filters, oscillators, and other electronic components. Analyzing AC circuits involves techniques like phasor analysis, impedance calculation, and the use of complex numbers. These methods simplify the process of solving for voltages, currents, and phase angles in circuits with multiple components. Mastering these analysis techniques is essential for electrical engineers and anyone working with AC systems. Measuring AC voltage and current requires special instruments like AC voltmeters and ammeters, which are designed to read RMS values. Oscilloscopes are used to visualize waveforms and measure properties like frequency, amplitude, and phase. Accurate measurement is essential for diagnosing problems and ensuring the safe operation of electrical systems. Working with AC circuits requires strict safety precautions due to the risk of electric shock and fire. Proper insulation, grounding, and circuit protection devices like fuses and circuit breakers are essential. Understanding the dangers and safety measures associated with AC helps prevent accidents and ensures the safe use of electrical equipment in homes and workplaces. Alternating current is used in countless applications, from powering homes and industries to running motors, lighting, and electronic devices. Its ability to be easily transformed and transmitted makes it the preferred choice for most electrical systems. Understanding the wide range of AC applications highlights its importance in modern life and technology. Harmonics are unwanted frequencies that are multiples of the fundamental frequency in an AC circuit. They can cause distortion, overheating, and reduced efficiency in electrical systems. Harmonics are especially problematic in circuits with nonlinear loads, such as computers and LED lighting. Understanding and controlling harmonics is important for maintaining power quality and protecting equipment. Filters are circuits designed to allow certain frequencies to pass while blocking others. In AC systems, filters are used to remove unwanted harmonics, noise, or to select specific frequencies for communication. Common types include low-pass, high-pass, bandpass, and bandstop filters. Understanding how filters work is essential for designing clean and efficient electrical and electronic systems. Rectification is the process of converting AC to DC using devices called rectifiers. This is essential for powering electronic devices that require direct current. Rectifiers can be half-wave or full-wave, depending on how much of the AC waveform they convert. Understanding rectification is key for designing power supplies and for understanding how AC can be adapted for different uses. Let's recap what we've learned about alternating current. We covered the definition and properties of AC, explored RMS and average values, phase differences, and the behavior of resistors, inductors, and capacitors in AC circuits. We discussed important concepts like reactance, impedance, resonance, power factor, and the principles of transformers and LC oscillations. We also looked at practical aspects, including transmission, safety, and applications. Mastering these concepts is essential for anyone studying or working with electricity. Congratulations on completing this comprehensive overview of alternating current. With a solid understanding of AC concepts, you're now equipped to tackle more advanced topics in electrical engineering and electronics. Continue exploring related subjects like electromagnetic waves, power electronics, and circuit design to deepen your knowledge. Remember, a strong foundation in AC is crucial for success in both academic studies and practical applications in the field of electricity.